go over a tutorial in Python over logistic regression. So if you remember in the previous video, we went over linear regression and how we classify or label data in a continuous range. Now in logistic regression, we are classifying and solving classification problem where our labels are discrete values. Before we get started, we need to make sure that we installed these packages. So the first package is the Vega datasets, which is the same dataset that we installed in the previous video. We would like also to make sure that we install these two packages, matplotlib and Seaborn, which are visualization packages we installed also in the previous video. If you installed all of these packages in the previous video, you should be fine. You do not need to install anything. In addition to that, we need sklearn, which is the machine learning package that we used also last time. So once you install all these packages on your Anaconda environment, let's get started by importing all of our packages. We will import pandas, we will import NumPy, we will import matplotlib, sklearn, model selection, so we can do the train test split. We will do the logistic regression, and the logistic regression, we will import the logistic regression, and it's part of sklearn from linear model. We will import metrics, which we will use to find and measure how our machine learning model is performing or how our hypothesis is performing. From Vega dataset, we will import the data so we can use the weather data. Remember, this matplotlib inline is a directive that we imported to tell the browser to display the plots inline within the HTML view that we see in the Jupyter Lab. I'll go ahead and compile this line or this cell, and it compiled successfully. Now the next step is importing Seattle weather data, and just if you view the description of this data, so I called, or I used the object data that we imported from Vega, and dot Seattle weather dataset, and then I try to print the description of the dataset, and this will display only numerical features or numerical variables within this dataset. So it shows 4 different variables. However, let's see the head of the first 5 rows, and this shows that we have 6 different variables. The first one is the date where this data has been captured, and the other 5 variables are some variables about the weather forecast in Seattle. So we have the precipitation, we have the temperature max, temperature min at that day, the wind, and the weather. So the weather description is drizzling, raining, and so on. Let's see what other features we have in the weather. Remember that this variable, we called it last time as categorical variable because the values of this variable are not numerical values. So we cannot apply any mathematical or logical operations on this variable values. So therefore, it's called categorical variable. So it has 5 different values. So we will use the weather in this example as the label to classify or try to predict how the weather will be using the precipitation, the temperature max, the temperature minimum, and the wind. So we will use these 4 variables to predict and train a classifier that predict how the weather will be. So initially, let's look at how many data points we have within our data set. So we have 1461. We have 1461 data points examples, and we have 6 variables. So let's see what the weather. We already have looked at the variables. So I'll just remove this line. We have seen that there are 5 different classes. So let's convert the weather from a categorical variable into a numerical value where we can use it in the form of numbers instead of using it as categorical variables or use it as a string. So remember from last video, we use the variable name from pandas data frame, and then we convert it to category, and then from category we get the cat and codes, and this will make sure our variable is encoded as a number. Let's see what will be the values within this wither code. So we will call dataset dot wither underscore code, which is the name that we picked for our variable, and then I will try to display the unique values to see what values we have. Now the values are, or the labels are, from 0 to 4. There are 5 variables. Let's display the head of this dataset just to make sure that we are going in the right direction. And now we see the weather code has been added. Drizzle will be 0, rain will be 2, and so on. Now I would like to check if I have any missing values or any values that has been assigned to null. So I use dataset.isNA. So this will create a Boolean matrix, and every value that have the null in it, or it's a missing, it will be replaced by true, otherwise will be false. So when I add all of these values using .sum, this will add up how many, or count how many missing values I have per variable. So now you see I do not have any missing values in this data set. Let's see how many values are null, not just missing. So I do not have any null values. Is null or is NA. It depends on the representation, or where you retrieve your data from, or what tool you use to retrieve your data. Sometimes the missing data points are represented in the form of NA, not available, and some other times they are represented in the form of null. So I used both of them just to make sure that I do not have any missing data points. Now let's keep the 4 variables: temp min, temp max, temp min. So we have, let's just go back, temp min, temp max. So this is temp max. We'll keep temp max, the wind, and the precipitation as values. These 4 variables, I will keep them as features to train our logistic regression. Then our label will be the weather code. You can keep the weather and use the string or the categorical variables for you as a label, and then build the classifier using that. However, when you do the metrics and the calculations, the Python will throw an error. So therefore, I would like to use the code. It's easier to deal with numbers rather than strings. Now I selected these 4 variables and I retrieved their values, and this dot values will convert my pandas data frame into a NumPy array. Similarly, I've done that for the weather code, the y, and I use dot value to convert it into a NumPy array. Now let's try to look at the distribution of our labels. So I decided to plot the weather code just to see the distribution of our data set, so that the classes. As you see in here, we have from 0, 1, 2, 3, 4. So we have 4 classes, if you remember, and it looks like class 4 is, we have many values from class 4. It's much more than other labels. So, and this, it looks like this data set is imbalanced. If you see in here, for a class 3, we have a very small number of data points, whereas in class 1 as well, it's much more than class 3. However, the examples for class 1, which is class 0 in this scenario, is very small. So therefore, since this data is, we call it imbalanced data set, where we have the number of examples per class is different. So we do not have the same number of examples for each class, which will create a biased model, and this model most likely will not perform well. So there are multiple methods of fixing this problem of imbalanced or unbalanced data set. So fixing these problems out of this video scope, but one of them is just, for instance, take label or randomly select the same number of values from each class. Like for instance, if we assume that the smallest class is class 3, so we go to class 3 and see how many data points I have. Let's assume we have 100. So we randomly select from class 4 100 data points. Then we already have 100 from class 3. We select randomly 100 data points from class 2, 100 data points randomly selected from class 1, and the same from class 0. So this will construct a balanced data set of 500 data points. Each class will have 100 examples, and this will be a balanced data set. There are other types of or other methods of balancing the data set, but this is a simple way of balancing the data set, given that we have largely enough data points from the smallest example, or the smallest, or the label with the least number of examples. So for this tutorial, I will just keep the data set as is. I will not try to balance it. So, but keep in mind, the results that we will have will not reflect how the model should be. Okay, so now we have seen the data set and it's imbalanced, which is a real life problem, as I said. So we would like to divide our data as we have done last time. So I partitioned and divided the data set into training and testing. 80% of the data will be for training and 20% for testing. So I used a train test split function, and then I provided the training data set as well as the labels for the training data set, or the overall data set in fact, and provided the split that I would like to use, or the test size that I would like to use, which is 20%. Before that, I printed the shape of my data set, and after that I printed the shape of both the training and testing as well as the labels for both. So as you see in here, the total number of data points for the overall data set is 1461. We have 4 features in the training data set, and we have 1461 in the labels, which is correct, and the X train and the Y train, which is the training data sets. X train is the actual training features, and Y train is the list of labels. So they are 1168, and we have 293 data points for testing. Now let's see, try to normalize our data. Remember last time we said it's a good idea to normalize the dataset or rescale the dataset and make it within a similar range, and make all of the features within a similar range. So therefore, we try to find the max and minimum for our dataset, and then our scaling will be subtracting the mean and dividing by the standard deviation. Let's run our code and see how the normalization has changed the range of our dataset, similar to what we have done last time. Now we would like to create our logistic regression, our model, and our model will use the object logistic regression. If you remember, we imported it up from sklearn. So now I created an object. This object is it's called, or from the class Logistic Regression. Then we have a few parameters that we can select from to change and play with the logistic regression flavor that you need to use in the training. So you can play with this based on the application that you are dealing with, based on the number of training example, how many classes you have. So the problem that we are solving in here is a multi-class problem. We have 5 different classes, and we would like to select the solver as liblinear. So this liblinear is the one versus rest. If you remember in the lecture, we talked about this type of classifier and how we can construct a multi-class classifier from logistic regression by using the method of one versus rest. So we'll keep the solver to be liblinear. We will use it. There are many other solvers that you can use. It depends on the number of labels that you have. For instance, if you are using a binary classifier, there are a set of solvers that you can use. And feel free to go to sklearn help for more information about the parameters and what are the possible values that you can use. For the sake of this tutorial, I will just keep them by default and just select these two parameters. The first one is the solver and the second one is the maximum iterations. If you remember, to find and calculate the list of theta parameters, or the parameters of our model, the model will use set of iterations. If you use a gradient descent, for instance, you will try to calculate theta in number of iterations. So I set the maximum number of iterations to be 1000, and this is the linear regression, or sorry, the logistic regression that we will use. After that, I took the regressor and I fit it on the training dataset. So I feed it with the training dataset, the features, and the second parameter is the list of labels. Let's run it, and now the logistic regression model has been trained successfully. So now, in this tutorial, I would like to see and show you something new that we haven't seen in the previous video. So we have something that's called accuracy. So accuracy, let's try to think about the accuracy first. Accuracy, it means how many data points within your testing data set, or within your data set, how many data points within your data set has been classified correctly, divided by the total number of data points that you used to test your model. So this is called accuracy. I listed in here, like I suggested, a link where you can read more about accuracy, or what we mean by accuracy. I also added what's called confusion matrix. Confusion matrix, it means for each one of the classes that we have. For instance, in our example, we have 5 different classes. It will show you for each class how many data points has been, or how many data points of each class the test data set included, and how the classifier classified each data points. For instance, if I have 100 data points in the dataset, the testing dataset from class 1, it will show me how many of these 100 data points has been classified as 1, which is the correct label, or how many of them has been misclassified as 2, how many of them has been misclassified as class 3, and so on. For instance, if I have a dataset that includes 2 classes, one is train and the other one is ship. So pictures, images for a train, ship, and car. So the confusion matrix now will have 3 columns and 3 rows. The 3 rows are the actual labels. So we have train, ship, and car. If we have, let's assume our testing dataset is 300 data points. So it will have 100 data point ship, 100 data point train, and 100 data point as a car. Now it will show me how many times from the ship has been classified as a ship, which is correct, and how many out of the 100 data points of the train has been classified as a ship, or how many, and it will show me how many data points out of the 100 data points of the train has been misclassified as a car. And this will help us adjust and fix our training dataset based on what has been misclassified as what. Okay, so and I added a link in here for the confusion matrix. Feel free to go and read more about the confusion matrix. So now, the first step that we would like to check in here, which is new, we would like to see how well the model is fitting our training dataset, or how well the hypothesis is fitting the training dataset. So therefore, what I will do in this step, I will take the training dataset. I have a model already trained or fit on a training dataset. Then I will take the same training dataset I used for training this model and try to classify it again and see how the model is performing. If you remember in the lecture, we talked about the overfitting problem. So this type of accuracy that we are calculating using the training data set, or the same data set that we trained the model on, it's called training accuracy. So training accuracy will give us an indication, are we overfitting the model, underfitting the model, or it's just right model for our parameters. So we will do this and calculate the training accuracy, which will find how much the model is fitting or fits the training dataset. Let's see how to do that. Remember that XTrain was our training dataset. So we will feed to the regressor to predict the labels for the XTrain and save the results in Y predict. So now we have, this is the set of features and this is the labels or the predicted labels for these features. I will use for metric or metrics the accuracy score. It's a function that calculates the accuracy. It will take how many data points with labeled correctly divided by the total number of labels. So then accuracy score will be the Y train, which are the actual ground truth labels, compared to the Y predict, which are the predicted values. And let's run it and see what's the accuracy. So our accuracy is 0.63.27, is almost 63%. 63% is fairly low accuracy. That means our model is under fitting. So I told you before, early at the beginning of this tutorial, that our dataset is imbalanced. So therefore, I expect that the model will not perform well. So therefore, this model is underfitted because the data is imbalanced. To fix this problem, we need to balance the dataset by either increasing the number of data points and make sure we have the same number of examples per class, or reduce the number of labels just to make sure we are having the same number of labels and then the same number of data points or examples per class. These two methods, one is called oversampling and one is downsampling, or upsampling or downsampling. These are most commonly used methods for balancing an imbalanced dataset. Now, this is an underfitted model, which is, for the sake of this tutorial, we will continue and proceed in this tutorial. But if it's a practical life application, you need to fix this problem, because this model will not perform well when you deploy it and put it in production. Now, we would like to retrieve the data and just plot the prediction versus the training, the prediction versus the actual labels. And let's take the first 20 data points and see how they look like. So you can see in here, this is the actual label, or the ground truth is 2, whereas the predicted is 1, and so on and so forth. You see the values. We have fairly good number of data points have been predicted correctly. This 4 and 4, 2 and 1 is incorrect, 4 and 4 is correct, and so on. Now let's go to the testing accuracy. The testing accuracy now will give us an indication how well our model is, and it will show us how it's performing on unseen data points. So if I got my accuracy in here, training accuracy, as 95%, now this is the first indication that our model is good. However, it might be overfitting. To determine and differentiate between this model is overfitting or it's a good model, we need to calculate the test accuracy. So the testing accuracy, if the testing accuracy is high and the training accuracy is high, that means we have a decent model. So what do I mean by high? Now, high is relative. It depends on the problem that you are solving and the number of examples that you have. If I have a binary classifier, so fairly good accuracy will be 95. But if I have a classifier with 1,000 data points, 1,000 different classes, so 70, 75 will be a decent accuracy. So, and all of this comes with the experience and practice to determine what is good and what's bad. Okay, let's see the testing accuracy. Remember that we kept 20% of the dataset unseen, and we will use this to calculate the testing accuracy. We fit it on, like we try to use it to predict, we predict the labels for the testing data set, and then we calculate the accuracy by comparing the predicted values versus the actual ground truth labels. And let's see what we have. So the accuracy in here is 53, which is close to the training accuracy. Again, the accuracy in here is very low, therefore this model is poor, and we know the reason. Because imbalanced data set. Now we kept the data points, the actual versus the predicted values. We displayed the first 20 of them. Let's try to plot them and compare them in a graphical representation. As you see in here, the blue is showing the actual and the orange shows the predicted. So you can see some of them, they are matching, like this one is predicted correctly, this one is predicted correctly, correct, this is incorrect, correct, and so on. Okay, so now before we end, let's see the confusion matrix that I mentioned, which is we have like for each class within the testing data set, how will the model we're classifying all of these data points. So we'll go to the confusion matrix, and this will plot the confusion matrix, and let's try to understand it correctly quickly in here. Again, the y-axis, the actual labels. So for instance, our data points, or we have from class 0 we have 11 data points. From class 1 in the testing data set we have 35 plus 42, which is 72 data points. In class 2 we have 32 and 27 testing data points, so we have this is 62. We have 62 data points from class 2. From class 3 we have 6 data points. From class 4 we have 122 plus 15. This will be 170 137. So 137 data points. As you see in here, class 4 is huge because the data set is imbalanced. Now, let's look, for instance, at the actual label where we have class 0. Now, you see we have set of columns. So this means we have 11 data points from class 1. 0 of them has been classified correctly. So the x-axis in here is the predicted label. So the predicted labels in here, out of the 11 data points in here from class 1 in the testing data set, 0 of them has been classified correctly. 0 of them has been classified as 1. 0 of the first class in the testing data set has been classified as 2. And 0 for class 3, and all of the first class data points, or the class 1 or class 0 data points in the testing data set has been classified as class 4. So all of this, if we assume this is car, all of the car images has been classified as, if 4 is the train, has been classified as train. So therefore, class 0 performs very bad, or this classifier performs very bad for classifying data points or instances from class 0. Let's look at class 1. So you remember we said we have 35 plus 42, which is 77. So we have 77 data points from class 1 in the testing data set. So 0 of these data points has been misclassified as class 0. We have 35 data points from class 1 has been classified correctly. And then 42 data points has been misclassified as class 4. So you can see is more than half of the testing data points of class 1 has been misclassified as class 4. If you look now at column 4, now I'm trying to read the results. So it looks like because the training dataset has been biased toward class 4, most of the data points has been classified to class 4. Why it's biased toward class 4? Because class 4 is the highest number of data points in the training dataset, I assume. If you look at class 4, For instance, and class 3 is similar to what we talked about class 1 and class 0. Let's jump to class 4. So we have in class 4, remember we said we have 172 data points in class 4 in the testing data set. So 122 data points from these 172 has been classified correctly. And this is due to the reason of biased data set. And only 15 data points from class 4 has been misclassified as class 1. So the confusion matrix is very important for calculating and trying to check the quality, study the quality of our classifier. For instance, if we know that the most important class that we would like to use or classify correctly in this classifier is class 4, then this classifier will be perfect. However, if we are giving equally likely weight to all of these labels or all of these classes, so then this classifier or this hypothesis performs very bad. So it depends on what's your ultimate goal or what's the goal of your classifier or your hypothesis. You can look at the results and try to interpret it, translate it. Like for instance, now I can see the data. This is another indication that the data set is imbalanced and requires more of pre-processing, more of investigation. Maybe I can divide the data into multiple types, or if this is the only data set that I have, or even select a different classifier different than the logistic regression. Or even I might be able to use some sort of advanced machine learning topics such as transfer learning to overcome this problem and produce much better accuracy. This is the end of this tutorial, and we'll see you in the next tutorial.